series. I'm going to try and go pretty quickly through this lesson. It's quite a long one, and I've actually got all the answers already filled in because the first time I tried to film it, it kind of broke down on me. So I'm going to try and go quickly. If you need to see something slower, you can always pause or you can rewind, but let's get into it. So, definition, geometric series is the terms of a geometric sequence expressed as a sum, is the definition the textbook uses. This should be pretty straightforward. The geometric sequence is, the simplest one is 1, 2, 4, 8, 16, so doubling every time, r equals 2. Geometric series now is, instead of doing that with the commas, we're just adding them all together. So 1 plus 2 plus 4 plus 8 plus 16, and it goes on and on like that. So that's fairly straightforward. Develop a formula for the sum of a series. So this is kind of like a definitional thing. We want to develop a formula so that we can add up all the terms together. And this one is more complex than the first one we looked at. That was the Gaussian sum one. This one's more complex, but it's also pretty fun. So why don't we actually try it? So first of all, we're going to write Sn. Which one do we want to do first? So the sum of the terms, we're going to write just the long version of the equation with all in reference into T1 or R. So our first term is T1, and to that we're going to add T1 times R. So you're taking your original term, you're multiplying it by whatever your R value is, that's your second term. To that you can add T1 R squared. So that's your third term. You multiply by R twice. And that kind of keep on going and going. And it gets all the way down to, what will the last term be? Well, this one started with T1. So the last terms, there was no R's here. The last term was actually going to be T1 R to the n minus 1. So 1 less than whatever our term number is. Term 1 had no R's. So term n has n minus 1 R's. So that's fairly straightforward. Now what we want to do is kind of really weird. What we have to do is multiply. We want to rewrite a second equation. We're actually going to put it on top for a reason we're going to say later. And our second equation is going to be the exact same as this one, just everything r times bigger. So we're actually going to do r times Sn. So we're just writing out, if that is the sum of a sequence, the sum of a geometric sequence, the sum of a geometric sequence times r. And we're going to shift this to the right a little bit. You're allowed to do that. So our first term is now going to be T1r. That makes sense. It's just T1 times r because it's r times bigger. Our second term is going to be T1r squared. And we're going to keep on going and keep on going. We're going to end up with a T1 r to the n minus 1 as our second to last term. And it's actually going to go one further. So we're going to add T1 times r to the n is going to be our final term. So now we've got two equations and both are true. This is the sum of a geometric series, and this is the sum of a geometric series times r, everything r times bigger. So both that's allowed, and now we're going to do something like elimination. We're going to do 1 subtract 2. We're going to subtract these two equations from each other. So on the left, we end up with Rsn minus Sn. And on the right, subtract that, so we end up actually with a negative T1. And then this term, subtract this term, so we've just shifted everything right because it makes the subtraction much easier. So this term should disappear, this term should disappear, all the terms in the middle should disappear, and we end up, so we get left over the first term, and we get left over this last term as well. So that subtract nothing should be plus T1 r to the n. And that's it. Now that we've subtracted these two equations from it, it still is true. This is a true expression, but we have to simplify it down. We want it to say Sn equals something in order to get what our final answer is going to be. So what we do for that is we're going to actually common factor Sn on the left, and that leaves behind an r minus 1. On the right, I'm just going to flip these terms because that's the way it shows in your equation anyway. T1r to the n is positive, subtract T1 is negative. And then all we have to do is actually divide by r minus 1. And that's pretty much it. So this is a really neat little trick for infinite series to develop formulas for them, or to come to an understanding of what a sum of them might be. I've seen this trick actually used in some much more complicated examples as well, so this is actually something that we like to do often in mathematics, is manipulate a formula a little way and then subtract them from each other, and you end up with, or add them to each other, you end up with something interesting. So this pretty much should be what you have on your formula sheet, except with just one difference. They common factored the T1. So they actually went one step further, and they said it's T1 on the outside. On the inside you have r to the n minus 1 all over r minus 1. And that's how you get to a formula for the sum of a geometric series. It's really complicated. I'm not going to test you on something like this, but hopefully you can kind of follow what was going on there. The math shouldn't be too bad. Knowing, like, actually coming up with the creative part is very challenging. But anyway, we get to our 3 different ones. We've moved on. This is the first one. So this is the little bit more complicated one. It doesn't have any reference to Tn. It only references T1, R, and N, are our 3 variables, all in relation to Sn. And then we have our formula 2. I forget which one's listed first on your sheet, but Sn equals R times Tn. So this whole term here, T1Rn, is actually the same thing as like the last term, right? Or T1R to the n minus 1 is actually the last term. So it's very close to the last term. So it's basically just swapping backwards. So this one is maybe a little bit easier to use, but you need to know what the final term is in the sequence to actually get that one. And actually, there's a fun fact about this. This one doesn't have any reference to n in it. This wasn't true for our arithmetic series formula. But in this one, we have r, we have tn, we have t1. You actually don't need to know how long the series is to use this formula. So this one, you know how long it is, but you don't know the final term. This one, you know the final term, but you don't know how long it is. So they both have their uses. Okay. So, first example. Sorry, a little bit hard to see on the webcam, but you've got your sheet to follow along. Determine the sum of the first 10 terms of each geometric series. So n is going to equal 10 because we're doing the first 10 terms, and we're looking for the sum this time. So we're looking for S of n. So in our example A, we have a couple things that we already know. We know n is equal to 10. We know our first term is 4. That's just fine. We know our r is 3. You do 12 divided by 4 for that, or 36 divided by 12. And what we're looking for is Sn. So we're going to be looking for that first version of the formula where we have the n, not the Tn. So write out the formula. Sn equals T1 bracket r to the n minus 1 all over r minus 1. And then sub in what you know. Again, I've done this all before because I already broke the video, but hopefully you can follow along. We're just subbing in our values, and then it becomes a calculator question. Hopefully your calculators, you can kind of do this all in one. You'll need quite a few brackets if you want to do it all at the same time. I kind of solve it in a couple steps. I usually do what's inside the brackets up here first, then multiply it by 4, then divide it by 2. But whichever way you're comfortable with, you should get to the answer S of n equals 118,096. So this is fairly straightforward. Just need to know what your variables are, pick your formula, plug in, and you should be able to get to the answer. In question B, so we're looking over there now, So what are our variables? It tells you t1 equals 5. It tells you r is a half. Again, n is 10 from the original part of the question, and we're looking for Sn. So this should be almost the exact same type of question. So you write out the formula, sub it into the formula, and you solve. And the solution should equal 9.99 if you've done that correctly. This one's fairly straightforward. Again, you can pause at any point, try these ahead of time. You should definitely at least try these at the end to see if you can calculate the right answer. Same answer that I'm going to do. This was not 9.99999, it was 9.990 something. But it looks like it's approaching 10, right? And in our next section, we're actually going to talk about infinite series that go on forever and ever. And this one, if this were an infinite series, it looks like it might actually be approaching 10 ultimately. But we'll test that next week, I suppose. Okay, question 2. This one should be one that you try on your own first, because it's pretty much the exact same as question 1, just some different numbers here. So determine the sum of the first 15 terms of this geometric series, 40, negative 20, plus 10. So we're flipping signs all the time, so you know what our value has to be negative then. And then you can find out what it is. So if you haven't yet, pause this video now, try and solve this question. Okay. I got these for our variables. N equals 15 from the question. We want 15 terms. Our first term is 40. Our R value is negative 0.5 or negative a half. Be careful with this one. It's not positive a half. It's not negative 2 or positive 2. Make sure you're calculating that right. So negative 20 divided by 40 should be negative a half. And we were looking for Sn. And then after that, everything is just like the last questions. So it's the same formula. You need to sub in what you know. And then this can be a little bit more difficult to solve. You need to be careful when you're subbing in. The negative r value needs to go inside brackets, inside its own set of brackets under the exponent 15. If you don't do that, the negative will act as a coefficient and it will change the answer. Hopefully you remember that from last year. This classic thing. If it's negative 2 squared versus negative 2 inside brackets squared. Very different answers. The top one actually equals negative 4, whereas the bottom one equals positive 4, because only the positive 2 is being squared in this top example, as opposed to the other one. Once you've subbed in, you need to solve, and you should get to roughly 26.67. So that question wasn't too bad either. So those were our straightforward ones. We're just subbing in the values to find the sum of the series. Example 2. So now we're going to start working backwards and doing some rearranging. The sum of the first 10 terms of a geometric series is negative 29,524. Yes, you can have negative sums. That works out just fine. The common ratio is negative 3. Determine the first term. So we're actually solving for T1 in this case. So, what do we know? T1 is what we're trying to solve for. We don't actually know that. Our R value is negative 3. Okay. We know S of 10. We know the sum of the first 10 terms is negative 29,524. And we also know the length of our series is going to be 10 terms long, n equals 10 as well. So this is, again, going to be the formula with the n, not the tn. So it's the same formula we were using up here. So we rewrite out the formula and sub in what we know. So we have the actual kind of y value, if you want to think of it like that. We have s of 10 on the left. T1 stays where it is, and everything else gets subbed in on the right. Now this isn't going to be too hard. This might look a little bit daunting to you if we're still just getting back into the swing of math. But so this is the variable we're trying to solve for. If we try and look at this in simple terms, it shouldn't be too scary. Basically, everything on the bottom is going to equal a single number. And whatever that number is, we can move over to the other side of the equal sign, ends up on top, and we're going to be multiplying negative 29 times whatever the bottom was. Same thing with everything up here on the top inside the brackets. All this is just a number as well. And when we simplify that down to a single number, it'll get moved over and we'll divide this number by it. Or you can do the division over here if you want to do it that way. But yeah, we're going to be just turning these into simple numbers and getting rid of them. So T1 is by itself is the goal. That's what I said here. So I calculated the top inside the brackets should equal 59,048. On the bottom it equals -4. And the bottom moves up, top moves down. And that's what you get for your answer. Should be actually just a simple number, T1 equals 2. Okay, we're going to try another one like this. This one is almost the exact same type of question again. They do 2 of every type. So this one you should try and pause and do on your own. The sum of the first 14 terms of a geometric series is 16,383. Common ratio is -2. Determine the first term. Exactly the same setup. So pause now, give it a try. Okay. So we know S of 14 is 16,383. We know our R value is -2. Sorry, it's a little bit sloppily written. R value equals -2. Our N is 14, of course, and our T1 is what we're looking for. So once again, it's the exact same formula. We sub in what we know. So it looks just like before. I'll explain the orange part later. And then you simplify and solve. T1 equals 3. So a nice round number. What I was doing here in the first video, I talked about if you're not getting to the correct answer, we need to problem solve where the problem is. So make sure you try, make sure you can actually get to the right answer, make sure you know how to put exponents in your calculator. My guess was if you're getting something different than 3 for your final answer, I would look right here as the most likely culprit of where you're doing things wrong. So the -2 has to be in its own set of brackets. All of it needs to be taken to the power 14. And this should be the very first step you do before you subtract the 1. If you're doing all that, fine. If you think you've done all that, fine. And you're still not getting to 3. We might need to check your work, maybe try and do this in multiple steps. If you were trying to do it all in one step before, try and break it down into smaller steps and see where the error is. We should get very comfortable with these calculations. This is obviously a big part of this unit. Okay, new type of question. Determine the sum of a geometric series for an unspecified number of terms. So now we do not know how long these series are, but we want to be able to solve them anyway. So in A, we start out with 1/27, 1/9, 1/3, and we go all the way up to 729, but we don't know how long that is. We could, of course, solve for how long that is. And that was actually the first thing I did here. Let me actually show that. Oh yeah, I talked about... I need another blank paper. Okay, first what we know. So we know our T1 is 1/27. We know our R value. So this one we should be trying to do with fractions because it starts out with fractions. So our R value, you could take the second number, 1/9, divide it by the first number, 1/27. It tells you a geometric series, so you actually only have to do one of them and you know they'll all be the same. If you don't, you might need to test more than one. Dividing fractions means kiss and flip. And then you do your cross-canceling. 27 and 9 both divide by 9. So it becomes 3/1. And the answer becomes 3. So our R value is 3. It's actually getting 3 times bigger every step of the way. We don't know what our sum is. That's what we're trying to find. The sum of the entire series. We do know our last term is 729. But we also don't know how long the series is either. We don't know n as well. So you could actually solve for n, and it's not too bad. You just have to use the formula we learned yesterday, or last week I guess it was. Tn equals T1 r to the n minus 1. But this actually isn't necessary, but I do want to talk you through it anyway, if you wanted to solve for what n was. Let's look at this anyway. So you would sub in what you do know. We have our final value, we have our T1, we have our R. So first thing you need to do is multiply by 27, bring the 27 to the other side, because this is the farthest thing on the outside, so it's actually the first thing to move. All this is stuck with the exponent. So that becomes 19,683 equals 3 to the n minus 1. And once again, we talked about this before, but there is no way to solve this without some mathematics called logarithms, which you'll learn in grade 12. The only other way you can do it is actually a guess and check method. So if you encounter a question like this where you're trying to solve for the exponent, you are actually stuck trying to guess and check. But that isn't too bad. You just put in 3 to the power of different values. So I think I started with like 3 to the power 7, and that didn't work out. It was too small. Then I did 3 to the power 10. It was too big. And then I tried 3 to the power 9 eventually, and that was exactly 19,683. So I replace 19,683 with 3 to the power 9. And I get 3 to the power 9 equals 3 to the n minus 1. And now this is actually this is an allowed step in algebra. It's kind of a weird step. You probably have never seen this before, so this is new grade 11 knowledge. If you have two bases and two exponents and they need to be equal, the bases are equal, that means the exponents must be equal. The only time these two expressions are going to be equal is when 9 is equal to n minus 1. Should be fairly straightforward, but sometimes you never know if things are allowed in math, and that is actually allowed. So n should be 10 in this case. I actually did all this because I forgot you don't need to know n for the second formula. But it's good to go over it anyway, so you can actually solve for n. It takes a little bit of work, but it's not too bad. Now the first formula is this one. So S of n equals r times your last term, subtract your first term, all over r minus 1. So let's sub in those values that we do know. R is 3, our last term is 729, our first term is 1/27, all divided by 2. And we're going to try and do this with fractions. Actually, I'm going to end up giving up eventually, but for now, let's try. You want to look at it. There's oftentimes the fractions will be a better answer. So you could do it two different ways at this point. You could try to simplify the top by finding a common denominator. So you could multiply this number by 27 and put it on a common denominator by 27 to simplify. But that's going to be not the easiest step. It's already going to turn our numbers pretty awful. There's actually another thing you could do, which is when you're dividing a polynomial, so multiple terms on top, if it all divides by 2, for instance, that means you actually divide each number by 2 individually. And that seems to be the easier way in this one, so that was the first thing I did. So I rewrote it 2187 divided by 2, subtract 1/27 divided by 2. Because I was still trying to keep the fractions, although it won't work for much longer. The first number actually doesn't simplify. It would turn into a decimal right away. And the second number is 1/52. Sorry. Why don't we just get rid of this now? So there is no way this is going to turn into a nice number. You would have to go back to here, and you would need to find a common denominator, and you would end up with a horrible, horrible denominator in the end. So fractions aren't very nice. If the fractions don't make it easier to see the number, then you can probably give up on them. So in this case, I don't want the denominator to be 50 seconds, and the numerator to be 10,000, 100,000s, I don't even know. If you multiply that by 52, I guess it's in the 10,000s. But it's not very nice. So at that point, I realized that it's probably going to be better just to give it as a decimal. Calculating this as a decimal, you should get 1,093 and 48 change, roughly. So that was rounded. Okay. If you like the challenge, you can try and do it as a fraction. Fractions are always appreciated. For questions I give you where I do want to see fractions, it'll usually end up being something nicer, like sevenths or halves or thirds or something like that. 50 seconds. That's pretty ugly. Try B. You should try B on your own. It's pretty much the exact same method. You should get a final answer. Again, you only have to do the one step because this formula you don't need to solve the n for. And you should get a final answer of negative 52,428. Okay, last page. And these are two fairly challenging word problems now. The first one's not too bad. Both of these take some interpretation, and both of these have a bit of a twist to them. So you need to be paying attention, and you need to already be comfortable with what we've been doing in this unit. So, the Western Scrabble Network is an organization whose goal is to promote the game of Scrabble. It offers internet tournaments throughout the year for WSN members to participate in. The format of these tournaments, it goes on to say it's an elimination tournament. So a lot of tournaments are elimination tournaments. It just means two people face each other, one will move on, and one will be out of the game. One will be out of the tournament. As opposed to round robin or double eliminate. There's a lot of other types out there. This is going to be the simplest one to analyze, so that's nice for us. The winners continue to play until there's a final champion. Now, there are 256 entries in the tournament. So 256 people enter the tournament. What is the total number of matches that will be played in the tournament? So we are not looking for how many people are left at the end. We're not looking for how many rounds. That's another type of question you could have. That's the type of question that you would have had yesterday. How many rounds are in this tournament? That would be solving for n. We are actually looking for the total number of matches in this tournament. So that should be our SN that we're looking for. The sum of the number of matches from all the rounds added up to each other. Now, the trickiest part of this, probably the only really hard part of this question, is it tells you there's 256 entrants. That is not going to be your T1 number. T1, in round 1, there are not 256 matches. Remember, we care about matches, not people. So round 1, there's actually going to be half that number. If there's 256 people, there's 128 matches in round 1. The rest of our variables. So it's good to actually write out a whole bunch of terms so you can kind of get an idea of how this is going to work. So if there's 128 matches in round 1, in round 2 there should be 64 matches. In round 3 there'll be 32, and it'll keep on going like that. And our very last round, we don't know what round it is, although we could solve for that pretty easily probably if we just continued the pattern. But in our very last round, we're going to have one match. There's going to be 2 people left. There'll be 1 match. And this will work out perfectly. These are powers of 2, if you didn't know that. If they weren't powers of 2, then we might end up with weird numbers down here. But this does work out nice. So they got the correct number of people to start the tournament with. So we have our Tn, we have our T1. Our R value is a half. Every time we're going to multiply the number of people or the number of matches by a half. It's always going to be half the previous number. Or you could just do 64 divided by 128. And we are looking for the Sn value. So we don't actually need to know what the n is. We can use that second formula, as I'm calling it. S of n equals r times Tn minus T1 all over r minus 1. And that should be just fine. And if you do that, the rest of this should be fairly straightforward, I think. You sub in what you know. R is a half. Tn is 1. It actually goes all the way down to 1. T1 is 128. Half minus 1 on the bottom. And it should simplify down to 255. There are 255 total matches. And this is a word problem, so we need a word answer. So therefore, there will be 255 matches played in total in this tournament. So the check marks, I was explaining this would probably be a 4-mark question if you saw it on the test. There'd be 1 mark for identifying your variables correctly. So this would be the hardest part of it. coming up that it's actually 128 in round 1 as opposed to something else. So did you get over that loop? So if you didn't figure this out right, you would just lose 1 mark, and hopefully you could do the rest of it correctly. 1 mark for using the correct formula and subbing in correctly. So these 2 steps, you identified the correct formula and you subbed in your values in the right places. That should be a really easy mark, hopefully. 1 mark for going from there to the correct answer. I know this could be a lot of math, but we have pretty good calculators these days. We should be able to do it in 1 or 2 or 3 steps. So just 1 mark for going from there to there, and 1 mark for writing the so therefore sentence at the end. Okay, the really hard question now. A person takes, and these type of question actually comes up fairly often, so there will be some on the homework that you see like this. I think question 15 in the homework is like this. Do you actually have to do 15? Oh, I don't think you actually did get assigned 15, but it's worth looking at it anyway. There's probably another one in the homework that looks like this anyway. A person takes a tablet to cure an ear infection. Each tablet contains 200 milligrams of an antibiotic. About 12% of the mass of the antibiotic remains in the body when the next tablet is taken. So that's the really important part. 12% is remaining when the next antibiotic is going to be taken by the patient. So you don't go down to 0 before you take a new tablet. You will actually constantly be building up how much of this antibiotic is in your system over time. It will go up and up and up, even though the amount it goes up is by a smaller and smaller amount. Determine the mass of the antibiotic in the body after 12 tablets has been taken. So this kind of question shows you that you do even need to know sequences and series if you're going to become a nurse, if you're going into nursing. And there's actually a lot of fairly advanced mathematics in nursing. So it's not just scientists and mathematicians that need this stuff. There's quite a few people. Engineers obviously need it and stuff. And even the business world use this quite often too. So we need to actually define some variables here at the very start because nothing's really defined for us and it's not super obvious. So I'm going to say let T1 be the amount in the body after 1 tablet is taken. So there's 2 different times you could be looking at it, like right before you take the next tablet or right after you take a tablet. So I'm going to be talking about right after you take a tablet. T1 means you've just taken 1 tablet. So you have the entire amount in your body. So that being said, we got to kind of go step by step here. T1 equals 200. At time 1, you have 200 milligrams of it in your body. At time 2, you take the amount of the first tablet and you multiply it by 12%. So 200 times 12%, which is going to be 24. Plus, you take a new tablet as well on top of the amount that you still have lingering. You take an additional 200. So you should have 224 in your body, milligrams of the antibiotic. Time 3, now this gets a little bit more confusing. I wrote it out in an interesting way. But basically, what you're going to be doing, there's a couple different ways to write it. The easy way to think of it is you're going to do the 224. You're going to multiply that by 12%, right? Because 12% of the amount from all your previous tablets will still be in your body. And then you're going to add another 200 to it. But I wrote it out this way so that we could see a pattern a little bit better. So I said at time 3, it's going to be, instead of 224, I wrote out the long version of 224. So 224 is all the first 2 steps times 12%. So take everything that you had in term 2, multiply that by 12%, and add an extra 200, just like we said. And that should equal 226.88. Now, this was my first instinct, and this is actually going to make the question, this is where the real challenge is. Is this a geometric sequence? 200, 224, 226.88? It might be. Let's calculate it. So 224 divided by 200 is 1.12, which makes sense. So you're multiplying it, it's the original amount, 100, and an extra 12%. But this one doesn't work out so nice. 226.88 divided by 224 is actually 1.0128. So this has a different R value. So this is not a geometric sequence. If you look at this as T1, T2, T3, this is not geometric, which means none of our formulas work for this. So the question is, what do we actually do about this? And the answer, once you see it, it's not too bad. I think it's hard to see at first, but I want to actually rewrite term 3. So let's rewrite term 3 and then we can see it a little bit easier. So let's actually expand this 12% into the brackets, which means this first term here becomes 200 times 12% squared. And then the second term here is 200 times 12%. And then we have our last term plus 200. So we should be able to see a pattern from here to here to here. And the pattern is, if you're looking closely, these aren't actually t values. These are actually s values. Every single value we were finding is actually the sum of all the previous terms. If we do it that way, this can actually be seen as a geometric series. So this is like our term 1 is 200, and our R value will end up being 12%, because this ends up being the 200 plus our 200 times 1R. This is 200 plus 200 times 1R plus 200 times 2Rs. So if we look at it that way, it actually makes sense. So to rewrite S3 the opposite direction, it's actually 200 plus 200R plus 200R squared. So it is actually like a series in that sense. And if we look at that, then we can define some variables. So our first term is then 200. Our R value is 12%, like we might have thought, not 1.12, because we're not doing the gaining. That's the plus part of this, but just 0.12. And the fact that it's a sum adds all the previous values into it. And we're looking for n equals 12. You could have found n equals 12 just by brute force if you just kept on going with this pattern, but that's not good math. We don't want to do it that way. So if we know these and we're searching for Sn, then everything should work out fine for us. So Sn is equal to, we're using the one, we don't know what the last term is, but we know n, r, and t1. So our first formula, we sub in the values we do know, and then from there it should be pretty straightforward. We just do our good old math, and we get to the final value. Oh, this was actually, I was having a lot of difficulty with this on the calculator. So the difficulty I was having was I was doing it in multiple steps. I did 12%, 0.12 to the power 12, which ended up being an incredibly small number. It was something like 8 point something times 10 to the power negative 21 or something. Really, really small number. Exponents either get very big or very small very fast. So this was so small, and then when I put in subtract 1, which is the next step, my calculator told me the answer was -1. It basically said this is practically 0 if you're going to talk about whole numbers like subtract 1. So that's no good. If you do it like that, you're not going to get the right answer. You do need to know what this value is. It does matter. It is sensitive. So it actually took me to put this entire equation into the calculator all at once in order to actually get the right answer. So I needed a lot of brackets. I needed a bracket around the entire top part. So I did bracket 200, bracket 0.12, bracket to the power 12 minus 1, bracket, divided by bracket 0.12 subtract 1 bracket. So it took a lot of steps, a lot of brackets, all to put it enter in at the same time. Please try this with your calculator. Make sure you can get to the right answer. The right answer should be 227.27 repeated. If you don't get that, if you get 200 or something, then your calculator wasn't calculating it right. You were missing some of the details in there. So please make sure you can actually get to the right answer. You can actually use the calculator correctly. And then the final step, word questions require word answers. So there will be 227.27 milligrams of antibiotic in the body still, in the body after he or she has taken 12 pills. Okay, if you're having trouble with any of these questions, again, let me know and I can walk you through some of them on the board. Other than that, you can go on to the homework.